Okay, let's start with the new lecture, new topic. In previous lecture, we discussed about the freewheeling diode, how freewheeling diode improves the input power factor. We have also discussed so far how to find out the output voltage waveform and the current waveform, the current expression under different load condition. Before we switch over to two-pulse converter, let us consider one more case, and that is again a single phase half wave converter, but now the load is only R and V, L and VC. There is no resistance in the load circuit. Problem is how to find out the current expression in this particular case. If the load is having a resistance only, we can say current is output voltage divided by the resistance. If the load is having inductance, we know how to find out the current expression. One is steady state, one transient, and then we can find out the current expression. Even if the load is having a DC source along with R and L, yes, there will be two steady state currents, one due to AC source, one due to DC source, and then there will be a transient component of the current, and then we can find out the final expression. Problem is, if there is no resistance, how to find out the steady state and the transient component. Now in this particular case, method of analysis remains the same. The voltage of anode with respect to this reference point, it will be a sinusoidal voltage, and the voltage of cathode with respect to this point, when it is replaced by an open switch, is same as a DC source. And like previous case, when this input voltage exceeds DC source, then only the thyristor is forward biased. And if I say this angle is theta, then the input voltage, which is root 2V sine of omega t, this input voltage is equal to VC at an angle theta, and therefore theta is sine inverse Vc upon root 2V. So the firing angle alpha, it should be more than theta, then only the thyristor can be turned on. Maybe somewhere here. By giving a short duration pulse, you can switch on the thyristor. And whenever the thyristor is turned on, the switch is closed, and then the output voltage follows the input voltage waveform. And before this, the output voltage was same as Vc. Now the question is, how long the conduction will continue? For that, we have to find out the current expression. Now in this particular case, during conduction, that is when omega t is more than alpha, your input voltage, which is root 2V sine of omega t, is equal to L di naught upon dt plus Vc. Now you cannot find out the steady state current and the transient current in this case, and then the current. The best way to find out the current expression is, since there is no resistive element, you can directly find out the current expression by integrating this. Let us integrate it from starting point alpha to general point omega t with respect to omega t. Remember, whenever you have to find out the current expression by integrating the differential equation, you should always start from the initial point to a general point, and we'll see why this. And when you are finding the average, then it is from the starting point till the end point. So it is alpha to omega t root 2v sine of omega t minus vc d omega t. Let's integrate this expression. You can multiply this by omega and divide it by omega. The way we did it to find out the average output voltage across inductance. Omega d omega t cancels with this d omega t. It will now reduce to integration of omega L with respect to I naught. So the limits will change. I naught at alpha and I naught at omega t, and that is equal to root 2v. It is minus cos omega t limits are alpha to omega t minus vc integration is omega t, limits are alpha to omega t. Left hand side it will become omega L. It is I naught at omega t minus I naught at alpha. It is a constant, so it is simply I naught, and the limits are I naught alpha and I naught omega t. This side it is root 2v. It will become cos alpha minus cos of omega t minus vc omega t minus alpha. What is this current? Current at I naught equals to alpha. This current is 0. The current is 0 at the instant when it is turned on. So this component is 0. It means the current at instant omega t is simply given by root 2v by omega L cos alpha minus cos of omega t, one term. Another is Vc upon omega L omega t minus alpha. This is how you can find out the current expression if the load is having inductance and a DC source and the resistance is not present. Let's plot this current. The current varies as per this expression. It starts with 0 initial value, becomes maximum and then becomes 0. At what instant it will become maximum? The current will become maximum when the voltage across the inductance is 0 because that is L di naught upon dt. So when the current has reached to the maximum, the voltage across the inductance will be 0. This is the input voltage, this is the DC voltage, and therefore if you see the load, output voltage is equal to the inductor voltage plus the DC voltage. It means the difference of the output voltage and the DC voltage, this is the inductor voltage. And this voltage becomes 0 at this particular point. It means the current will become maximum at this point. It will not be sinusoidal, it depends on this particular expression. And then the current decreases, it may become 0 somewhere here. During this period, inductor has stored the energy. During this period, inductor has released the stored energy. So that the average voltage across the inductance is 0. Now, as long as current is flowing, the output voltage follows the input voltage waveform. And when the current becomes 0, output voltage becomes. If you see the voltage across the inductor, it is this vertical distance, and during this it is positive, and this vertical distance which is negative, and since the average voltage across the inductance is 0, the area of this is equal to area of this. This is the angle beta up to which conduction will take place, and this beta angle you can find out from here. That I naught at beta is 0, and that is root 2b by omega L cos alpha minus cos of beta Vc upon omega L beta minus A. Just by hit and trial method, you can solve this equation knowing all parameters except beta, and you can find out what is the beta value. Once you have the beta value, you can also find out the average output voltage. By definition, average output voltage is area under the curve from 0 to 2 pi and integrated from 0 to 2 pi divided by 2 pi, that gives you the average output voltage. So it is 1 upon 2 pi from 0 to alpha, it is same as Vc. From alpha to beta, it is same as input voltage. And again from beta to 2 pi, it is same as Vc. Let's modify this. If we subtract Vc in this one and add Vc also, this becomes 0 to alpha Vc d omega t, alpha to beta, it is root 2v sine of omega t minus Vc d omega t, we have subtracted, so we have to add a term also, Vc d omega t, and the last term is integration of Vc from beta to 2 pi d omega t. 0 to alpha, alpha to beta, beta to 2 pi. So this becomes 0 to 2 pi Vc d omega t. And this term remains as such, alpha to beta root 2v sine of omega t minus Vc d omega t. What this particular term indicates? This indicates the average voltage across DC source, and it is Vc into 2 pi divided by 2 pi, it becomes Vc. What the second term indicates, it is 1 upon 2 pi alpha to beta root 2v sine of omega t minus Vc d omega t. It is root 2v sine omega t minus Vc, that is the voltage across the inductance, and that voltage is from alpha to beta divided by 2 pi, so it is the average voltage across inductance, and it has to be 0. Just put the integrated, so it is Vc plus 1 upon 2 pi root 2v minus cos omega t, limits alpha to beta, so it is cos alpha minus cos of beta, then minus Vc, integration will give you omega t, limits alpha to beta, so it is beta minus alpha. From the previous current expression, this is 0 and therefore it is Vc. It means average output voltage is same as Vc, which is what we expect, because instantaneous output voltage is instantaneous voltage across inductance plus DC source. So the average output voltage is average voltage across inductance plus DC source. Average voltage across inductance is 0. Average output voltage is same as Vc. So the average output voltage is given by this particular one, and how much power goes to this particular DC source, that we can find out, because this is the standard circuit used to charge a battery. By putting a small inductor, we can make the current nearly continuous, and then the battery is charged. So if you want to find out the power output, instantaneous power is the instantaneous voltage into instantaneous current, and the average power is 1 upon 2 pi 0 to 2 pi this thing I naught d omega t. And what is this? It is a constant voltage 1 upon 2 pi 0 to 2 pi I naught. This is the average current. So the power which is going to the battery is Vc into I naught. Question is now how to find out the average current. Now there is no resistance, and therefore you cannot find out the average voltage across resistance. It is not available, and if this is not there, you cannot find out average output current like VR by R. This is not possible in this case. The only method which is possible is fundamental, and that is, you have the current expression, integrate that current expression and that is 1 upon 2 pi alpha to beta root 2v upon omega L cos alpha minus cos of omega t minus Vc upon omega L omega t minus alpha. This expression is to be integrated with respect to omega t from alpha to beta divided by 2 pi. That gives you I naught. Put it here, you can find out the power which is going to the DC source. There is one more possibility, and that is only inductor is present in the load circuit. Only inductor. No resistance, no DC source. What happens in this particular case? You have input like this. It is clear that the thyristor is forward biased in the positive half cycle, and therefore at alpha angle you can trigger the thyristor. Whenever this thyristor is triggered, output voltage follows the input voltage waveform, and therefore the input voltage, which is root 2v sine of omega t, that is equal to L di naught upon dt. To find out the current expression, integrate it from alpha to omega t. This side will become root 2v cos alpha minus cos of omega t, and on this side omega L upon d omega t, this will cancel. Integration of omega L with respect to I naught, limits will be I naught at alpha, I naught at omega t, and therefore it will become omega L I naught at omega t minus I naught at alpha. Certainly at the initial current is 0, and therefore I naught expression is root 2v by omega L cos alpha minus cos of omega. And if you plot the current, it is 0 up to this point, then it increases and it becomes maximum at pi, because this is the instant when the voltage output or the voltage across the inductor becomes 0, and then the current decreases, becomes 0. As long as conduction is there, output follows the input. Whatever is the output voltage, same is the voltage across inductance. And since the inductor average voltage is 0, so the area of this particular curve, this is the positive one, is equal to this negative area, then only the average voltage across inductor will be 0. And if these two areas are same, we can say if this is the angle alpha, this should also be alpha. It means beta is equal to 2 pi minus alpha. Beta is equal to 2 pi minus alpha. This is how you can analyze a single phase circuit. I have discussed all possible cases, and in rest of the course, this is the standard method of finding the current, whether it is a converter, an inverter, a chopper, or any other power electronics circuit. Let us consider now a 2-pulse midpoint converter. Now in this single phase converter, whatever may be the nature of the load, a single phase supply is applied like this. Now question is from where this supply comes. Normally at the input you have a step down transformer. It may be a step up transformer also, and then you have the thyristor and the load. This is how this input supply is actually obtained. Why this transformer is required? It's a 2-winding transformer. One reason is isolation. You want to isolate the source and the load. And the second reason is matching the output voltage with the load requirement. When the firing angle is minimum, output voltage is maximum. That maximum output voltage should be equal to the voltage rating of the load. And to match the maximum output voltage with the voltage rating of the load, you may either have to step down the voltage or step up the voltage. And if the voltages are proper, then only for the isolation purpose you need a 2-winding transformer. So the transformer is must at the input of the converter. Now what is the problem? If you look at this particular circuit, whatever may be the nature of the load, this current I0, current may be like this with resistive load, current may be like this with inductive load, and even if you have connected a freewheeling diode, the current will flow only from here to here and then become zero, only freewheeling action will take place. Whatever may be the case, you can see all these three currents, they have an average value. Average value means a DC current. So a DC current is flowing through the secondary. This output current is same as input, and therefore a DC current is flowing in this one along with harmonics. Now as far as DC current is concerned, it is a unidirectional current. Now when the unidirectional current flows through the secondary of the transformer, transformer gets saturated, and because of the saturation, the voltage, the output voltage will no longer remain sinusoidal, it gets distorted. So this current leads to saturation of transformer, and that basically distorts the source voltage or the input voltage. Now if you want to avoid this distortion, then there should not be any average current flow through the secondary of the transformer, and that is possible if we go from this half wave converter to full wave converter, or you can say single pulse converter to two pulse converter. So the first one is a two pulse midpoint converter. Why it is called midpoint converter? Because there is a transformer and that transformer is having a center tap secondary. That's why it is called midpoint converter. Two thyristors are connected like this. Common terminal, and then you have a load which is connected between this point and the center point of the transformer. This is say TH1 and this is TH2. This is the source voltage, and let us say this is the voltage V1 and this is the voltage V2. Now the voltages are with respect to this center point. Both V1 and V2, they are equal in magnitude, but they are opposite in phase. This is the output voltage and the output current. Basic operation remains the same, no change. Whenever a thyristor is forward biased, it can be turned on by giving a short duration pulse between a gate and the cathode, and then the thyristor goes into conduction. And when the current through thyristor becomes zero, the thyristor is switched off. Remember, in the previous cases, in the previous configuration, the current automatically becomes zero at certain point beta angle, and then the thyristor is switched off. One of the condition or the necessary condition for the commutation is the current through thyristor be reduced to zero, and then it should be reverse bias for certain minimum period. And we have seen how that reverse bias appears when the current becomes zero. There is another way also. You just apply a reverse voltage across the thyristor, and then the thyristor current becomes zero, and then the thyristor gets commutated. Let us see what happens in this case. First,